Hello and
Recording in
welcome back
progress.
to our practice in converting from one concentration unit to another. We are still looking at the saline bag, same example, right? We were given the mass volume percent of our sodium chloride in our saline bag. We were given some other pieces of information that could or could not be useful, including the density of the solution. And we are being asked to convert this from one concentration unit, the mass volume percent, to another. So in our previous video, we looked at how we could convert this mass volume percent from mass volume percent into molarity. So in this part of our exercise, we are seeing if we can't convert it into molality. So our goal is to get molality. So let's probably remind ourselves of what molality is. Molality is moles of solute per kilogram solution. And if you think back to like what we assumed, so let's keep that assumption going. We assume that we have 1,000 mils of solution because that's what it says here on our little label. If we keep going with that assumption and we think back to our molarity calculations, we will find that we already know our moles of solute. So going back to our work on the previous page, we took the 1,000 mils of solution and utilized the mass volume percent, which tells us the grams of solute per mil solution. And then once we had our grams of solute, we divided by the molar mass to get our moles, which was 0.15400. Again, chems are two things. They are cheap and lazy. So let's reuse that number. We're making the same assumption, right? We're still assuming that we've got one bag, which is 1,000 mils. So we know already from our prior calculations that in that 1,000 milliliters of solution, there must be 0.154 moles of sodium chloride. So I'm going to recycle that. So we already know that we have 0.154 moles sodium chloride. So we know our numerator. Now our task is to figure out something about, what have I done here? See, you get so used to writing solution. We need to remember molality is kilograms of solvent. Always write in all caps when I want to get myself to remember that. There we go. So now that I've got my moles, my solute, my numerator, we need to find just the mass of solvent. Or water. And a good thing to remind ourselves of anytime we're talking about masses of solutions or component of solutions is the law of conservation of mass, meaning the mass of the solution in total is equal to the mass of the solute plus the mass of the solvent. I mix two things, their total mass in sum is equal to the mass of the resulting mixture. That's all we're saying here. So let's maybe look at this a little bit closer, right? We're trying to find mass of solvent. So we could rearrange this so that we get mass of solvent is equal to the mass of the overall solution minus the mass of the solute. And again, chemists are cheap and lazy. Where did we get our moles of sodium chloride from when we assumed we had 1,000 mils of solution? Going back to our prior work, we know the mass of sodium chloride from our mass volume percent. So we already know how many moles should be, or excuse me, how many grams should be present. So let's rewrite it. But the idea is once you have made an assumption, stick with it. Like reuse the information that you know about the extensive properties of that solution. So here we're trying to find mass of solvent, that's the mass of water. And we're first going to work on finding the mass of solute. So we had 1,000 grams of solution. And then we knew we had 0.009 grams NaCl per 1 mil of solution. That was my mass volume percent of saline, just expressed as a decimal instead of a percentage. Okay. So if I take 0.009 and multiply it by 1,000, that's moving my decimal over 3 places. So that's equal to 9 grams of solute. So I have a mass of solute, which means I am halfway there in terms of figuring out my desired mass of solvent. So that leaves us with our mass of solution. Let's go back to the problem. I need to now figure out what I know about the solution. So first and foremost, I have what I assumed about the solution, right? So I know the volume of solution. I know that we have 1,000 milliliters of solution. And if I'm trying to get the mass of solution from my volume of solution, I need to think about some kind of conversion factor that relates mass of substance to volume of substance. And as we've discussed, that conversion factor is density. So this tells me how many grams of solution I can pack per milliliter of solution. So I'm already in milliliters here. I know, according to my density, that if I had 1 milliliter of solution, that should weigh 1.0046 grams. See how it is helpful to label whether you're talking about solution or solute or solvent. So again, this is nice because this allows us to take 1,000. So move over 1, 2, 3. This is 1,000. One zero zero extra 0, 1,004.6. Let's see here. 1, 2, 3. Yep. Grams of solution. So now if we want to find the mass of solvent, which is our water, that is going to be our 1,004.6 grams of total solution mass, subtracting out the 9 grams of solute. So 1,004.6 minus 9 gives us 995.6. And this is grams of solvent. So good, I've got something that relates to my solvent. And now the question is, if I look back at my molality, do I have my units straight? So I have my moles, molality, of solutes. And I do have a mass of solvent. However, this mass of solvent is not in the correct unit, right? Molality demands that we use kilograms of solvent. So if I want to take grams and convert to kilograms, that is moving my decimal over 1, 2, 3 places. So this is equal to 0.9956 kilograms of H2O. And now I have the extensive properties needed to get a proportion of to determine my molality. So let's do kind of our final steps on this next page here. So we wanted the molality of the solution, which again was our moles of our sodium chloride over the mass in kilograms of our solvent. We had solved for these respective quantities in our prior work. So we knew in our assumed 1,000 ml sample of saline, there were 0.154 moles of sodium chloride. And then from our work determining our mass of solvent in kilograms, that was 0.9956. Carrying all digits, not rounding preemptively. Kilograms of H2O. So we've got 0.154 divided by 0.9956 equals 0.15468 molal. And then to the correct significant figures is an interesting one. I probably should have given us some more digits here because that's only one sig fig. So let's just use 3 so that we can make a nice distinction between molarity and molality because oftentimes their values are similar. So our molality is 0.15 rounding up 5 molal. So that is our molality. Now, why is this so similar to the molarity? Right here, molarity, right? 0.154 molar versus 0.155 molal. That's because we're talking about aqueous solutions here, right? So this total mass of water, the like 0.995 or 1 kilogram, is approximately equal to, 995 milliliters of water, which is really close to the total volume of solution, right? Because the density of water is 1. So you will often see that in aqueous solutions, molality and molarity might come out to be really similar, but they are not the same. So just kind of pay attention to that. So in our next video, we will be looking again at this saline solution, except we will now utilize a conversion to mole fraction, which is something that we have seen when talking about our colligative properties lab, right? We needed to build a plot of mole fraction against massive solution lost. So let's see if we can't convert a known quantity of a 0.9 mass per volume percent saline solution into a mole fraction of saline in our next video. See you then.